The Global Positioning System, or GPS, is a satellite-based navigation system, developed and maintained by the United States Department of Defense. Initially designed for military purposes, it was later made available for civilian use and has become essential for global navigation, timing, and positioning services. How GPS works. GPS operates using a constellation of satellites, ground control stations, and user receivers, for instance smartphones and car navigation systems. The system determines a user's precise location, latitude, longitude, and altitude, and ensures time synchronization by measuring the time it takes for signals from multiple satellites to reach the receiver. The key components of GPS are the space segment, the control segment, and the user segment. The space segment. This segment consists of at least 24 satellites orbiting at an altitude of approximately 20,200 kilometers at a speed of nearly 4 kilometers per second. Satellites are arranged in 6 orbital planes, ensuring that at least 4 satellites are visible from any point on Earth. Each satellite transmits radio signals containing precise timing and orbital data. The control segment. This includes a master control station, monitoring stations, and ground antennas. These facilities track satellites, correct their orbits, synchronize atomic clocks, and update navigation data. The user segment. This segment consists of GPS receivers embedded in various devices. Receivers process signals from multiple satellites to calculate the user's 3D position and precise time using trilateration. Technical details of GPS operations. GPS satellites carry highly stable atomic clocks, synchronized with one another and with reference atomic clocks at the ground control stations. Any drift of the clocks aboard the satellites, from the reference time maintained at the ground stations, is corrected regularly. Since the speed of radio waves, namely the speed of light, is constant and independent of the satellite's velocity, the time delay between when the satellite transmits a signal and the receiver picks it up is proportional to the distance from the satellite to the receiver. Using distance information collected from multiple satellites, the location coordinates of any GPS receiver can be calculated with great precision. Relativistic effects and GPS. It is widely claimed that GPS provides a clear verification of both special and general relativity. The idea of testing general relativity using atomic clocks on Earth satellites was first proposed in 1954 by physicist Friedrich Winterberg. It is calculated that a clock moving at the speed of GPS satellites relative to the Earth's surface, and at their orbital altitude, would gain approximately 38.6 microseconds per day, relative to clocks on the ground. This discrepancy results from two relativistic effects, a time dilation of 7.2 microseconds per day, due to special relativity, and a time acceleration of 45.8 microseconds per day, due to general relativity. It is often stated, even by authoritative sources, that failing to account for these effects would result in an error in positioning of nearly 12 kilometers per day. To compensate for this discrepancy, the frequency standard on board each satellite is pre-adjusted before launch, ensuring it runs slightly slower than the desired frequency on Earth. The fact that GPS positioning functions accurately is frequently cited as strong evidence for the validity of special and general relativity. Dissenting from this narrative is often met with skepticism or dismissal. However, does this narrative hold up under scrutiny? A closer examination of the equations governing GPS positioning reveals that, even if relativistic corrections were not applied, the GPS system would still function with acceptable accuracy. This challenges the notion that GPS serves as definitive proof of relativistic effects, and opens the door for deeper discussion on the topic. As a matter of fact, the receiver uses messages received from at least 4 satellites to determine the satellite positions and the time the messages were sent. The Cartesian coordinates of the satellite position and the time sent are designated as xi, yi, zi, and small si, where the subscript I denotes the satellite and takes the value 1, 2, 3 to n, where n is greater than or equal to 4. When the time of message reception indicated by the onboard receiver clock is capital Ti, the true reception time is small ti equals capital Ti minus b, where b is the receiver's clock bias from the much more accurate GPS clocks employed by the satellites. The receiver clock bias B is the same for all received satellite signals, since we are told that the satellite clocks are all perfectly synchronized. The message's transit time is capital TI minus B minus small si, where small si is the satellite time. Assuming the message traveled at the speed of light c, the distance traveled di is di equals capital TI minus B minus si times the velocity of light. For 4 satellites, the equations to satisfy are these, where di is the geometric distance, or range, between the receiver and satellite I. The values, x, y, z, without subscripts, are the Cartesian coordinates of the receiver's position. Since the equations have 4 unknowns, x, y, z, b, namely the 3 components of the GPS receiver position and the clock bias, the signals from at least 4 satellites are necessary to attempt solving these equations. They can be solved by algebraic or numerical methods. All this means that, no matter how large the bias of the receiver's clock is, relative to the GPS clocks employed by the satellites, the position x, y, z of the receiver will always be well determined. The bias B could be equal to, greater than, or smaller than the alleged relativistic effects on satellite time, and it would make no difference at all to the precision. Therefore, the perfect functioning of the global positioning system does not prove relativity. The only effect of the absence of relativistic corrections, as already calculated by Winterberg, would be that, over the course of a year, the clock on the satellite would be 0.0042 seconds behind the clock on Earth, namely, a 0.042 second difference in 10 years. Unfortunately, even this effect would not be measurable, since the atomic clocks used onboard GPS satellites are not that stable. They must be updated twice per day to correct the clock's natural drift. In the literature, it is said that these periodic corrections are tiny, on the order of 1 nanosecond, 3 orders of magnitude smaller than what would be needed to make the relativistic effects unnoticeable. However, if the real periodic corrections were that low, there would be a problem with mutual desynchronization of all GPS satellites. Anomalies in satellite synchronization. It is said that all GPS satellites are synchronized once and for all at their launch, and remain synchronized despite moving in different orbits with different relative velocities. Special relativity suggests they should experience time dilation relative to each other. Note that the satellite's orbital motion is technically a freefall motion, and, as such, represents an inertial reference frame. Special relativity can and should be applied. In fact, freefall motion makes the reference frame even more inertial than any stationary reference frame on the Earth's surface. However, allegedly, no such desynchronization occurs, nor is any correction implemented for this. In that case, only the special relativistic contribution should operate, and, according to the orbital geometry and relative velocities, it could well happen that between 2 satellites, a desynchronization of 7 microseconds per day, or even higher, should occur. Why does such a desynchronization, required by special relativity, not appear? And, if it does exist, periodic clock corrections by ground stations must be higher than what is commonly stated, on the order of several microseconds per day, enough to make the alleged relativistic effects unnoticeable, and their correction before the satellite's launch unnecessary for the effective functioning of the GPS system.